technology, a large number of new particles were discovered.
1946年以后呢，这个加速器还有侦测器的技术有长足的发展。我们有所谓的同步回旋加速器，我们有同步加速器。那 detect 部分我们有这个气泡式，还有闪烁计数器等等这些新的技术。那不过我们没有办法讲太多的细节。这边的重点是呢，你有这些新技术以后呢，一个很不幸的事情就发现了，就是我们突然发现了很多的基本粒子。
And this is the beginning of the quark model. Because of these new particles, physicists wondered what to do with them. And finally, Gell-Mann and Neyman, independently in 1961, proposed a classification scheme that would organize these particles called the eightfold wave, based on a mathematical model only. But this was called the periodic table of the particles. And the interesting thing about this particular classification scheme, just like the periodic table of the elements, it was both descriptive and predictive. In other words, it explained the current particles discovered, and it predicted the existence of new particles that had not yet been discovered.
那就像刚刚说过，因为新技术的发展呢，我们突然发现一大堆莫名其妙的这个基本粒子。那时候表曼跟尼玛他们就发现了，其实这些乱七八糟的粒子呢，可以分类跟整理成非常漂亮的规则，就跟化学里面的元素周期表一样。OK， 那门德列夫当初弄出这个化学周期表成功以后呢，他也可以 predict 在什么地方、什么重量、什么样化学特性可以找到一个新的元素。那的确有很多新的元素是这样子被发现。同样的呢，这个表曼跟尼曼他们发明的这个分类方法，所谓的 FOA 或八正道，它也除了可以把所有那时候看到的粒子做很漂亮的分类以外呢，在有一些空位的地方呢，它也预测了一些那时候还没看到的粒子的存在。
And here are the families. There's a family, each family has a different spin. The particles have the equivalent of rotational motion called angular momentum. And you basically have different particles have different amounts, and they are assigned by quantum mechanics. I won't get into that, it's not important. But the point is, there's a family for zero spin, we call it spin, zero spin, spin 1, spin 1/2, spin 3/2. Now, every one of these families have particles. You see, every dot is a particle. All these particles were ultimately discovered.
Okay. 那刚刚提到这个八正道的分类呢，就可以把当时的粒子呢，按照它们的角动量大小分类排成这个非常特别有趣的形状。那从这个没有角动量 spin 里 ，spin 是它自己的自旋，到 spin 1/2到3/2，这些点呢都是那时候已经被观察到的粒子。那个画红圈的，等一下 Friedman 会告诉大家。
But then the question arose, why is this scheme so successful? There is no physics in it. It is just a mathematical model, and people started to worry about how to explain the success of this classification scheme. And so, in order to basically explain it, the quark model was proposed by Gell-Mann and Zweig independently. And they were proposed as the building blocks of all these particles. And the quarks gave the structures and the symmetries of the various families, and I will demonstrate it to you in a subsequent slide of how that worked.
一个很基本的问题就是，刚刚这个分类或者这么奇妙的这个规则是怎么产生出来的呢？那在1964年呢，这个表曼跟Laureate他们就提了一个 model， 是所谓的 Quark model， 它基本上是要解释为什么这个八正道这么棒。那
So what was the quark model? there were three types of quarks in those days: the up quark, the down quark, and the strange quark. They all had they were spin 1/2. They all had fractional charges. The up was charged was plus 2/3. The down was minus 1/3, and the strange was minus 1/3. Now this is for example, a proton has a charge +1, an electron has a charge -1, and you see these are fractions, and this was considered extremely strange and unacceptable at that time. Physicists said there are no particles in nature of fractional charge, and it was therefore largely rejected by the physics community. Now let me show you how this works. The proton on the left consists of two up quarks and a down quark. So the charges are 2/3 plus 2/3 is 4/3, minus 1/3 is 1. If you look at the neutron, it's one up quark and two down quarks. So plus 2/3 minus 1/3 minus 1/3 is 0. And that's how it worked.
OK， 那有没有跟泽维他们的回答呢？就是这个 pattern 呢，基本上就跟周期表一样。周期表它之所以最后会长成这样，基本上是由质子、中子跟电子的组合而成。那刚刚看到八正道基本上是由3种夸克所构成的。那他那时候的这个理论呢，一共有3种夸克：上夸克、下夸克跟奇异夸克。那它们有非常奇妙的电荷。上夸克有2/3的质子的电荷，下夸克跟奇异夸克呢有-1/3的质子的电荷。那大家可以看底下这2个例子，看为什么这个夸克模型这么的成功。我们知道质子的电荷是正1，所以你把2个上夸克加1个下夸克，它的电荷是2乘以2/3减掉1/3，刚好是1。那中子是没有电荷的，所以有一个上夸克加上2个下夸克的话呢，刚好它的电荷是2/3减2乘以-1/3等于0。所以
So this is how it worked. You see, if you look at this, this is the spin 3/2 family. And if you look at the very top, it's made up of 3 strange quarks. The second line is 2 strange quarks. The third line is 1 strange quark. And then the fourth line is no strange quarks. If you look at this corner, you have 3 up quarks, 2 up quarks, 1 up quark, no up quarks. And the same thing with the other corner. 3 down quarks, 2 down quarks, 1 down quark, no down quarks. And you see, that is how the quarks gave the structure of the family. You don't need fancy mathematics to see this.
OK， 那我们可以从这个自旋3/2的家族来看看这个夸克模型是如何成功。你可以从金字塔顶端数下来，它顶端呢一共有3个奇异夸克，第2行呢有2个奇异夸克，第3行1个，最底下呢没有。你如果从斜边开始数的话呢，斜边，OK， 那你可以从这个三角形的另外一边数的话，你可以看到上夸克跟下夸克，它每隔1行数目就增多或减少，所以你不需要什么很特别、很奇妙的机制，你就可以用3个简单的夸克呢，把刚刚所有发现这些乱七八糟的基本粒子通通弄出来。
But the question is, are quarks real? What do physicists do when a new particle is proposed? They search for it. They search everywhere. They search at accelerators, in cosmic rays, in meteorites, in water, everywhere, and not a quark could be found anywhere. And so people say, well, that's expected because it's a crazy idea. The idea of having fractional point-length particles making up the proton and neutron doesn't make any sense. And it was largely rejected, as I said, but it was thought to be a good mathematical representation, but not real.
所以夸克模型出来以后呢，就那时候光能物理界就有很多的搜寻。那你可以从加速器，你可以在这个宇宙射线，在海水、空气 这叫什么陨石还有各种人造的环境里面都没有找到带有分数电荷的夸克存在。那大家都那时候的一般的看法都是觉得提出一个带有分数电荷的东西，基本上是就够了所以大家的一般的看法都是这个夸克模型基本上只是一个数学模型，而不是真的。
So let's give you an example of what the opinions were. Murray Gell-Mann, who was the father of the quark model, or one of the fathers, he said the idea that mesons and baryons, these various particles, are made up primarily of quarks is hard to believe. That's the father of the quark model. James Bjorkane, who was also working in that area, said additional data are necessary and very welcome to destroy the picture of elementary constituents, namely the quark model. Kurt Gottfried, who was also working in this area, said, I think Professor Bjorkane and I constructed some rules in the hope of destroying the quark model. And then J.J. Kokeny, who was a theorist at CERN who wrote a whole book on quark, at the end said, of course, the whole quark idea is ill-founded.
OK， 那时候的物理学家呢，基本上对夸克模型是完全不相信。大家可以看到第一个引的呢是Gell-Mann他自己的 comment， 那个夸克模型是他发现，他说你这个所谓的介子跟 baryon 粽子吧，谢谢，是由这个夸克构成的这件事情呢，我自己都无法相信。然后其他的科学家更不用说，那底下有3位那时候很著名的科学家，基本上都是持一面倒的反对态度，这个东西不可能存在的。
So what was the idea? What did they think protons and neutrons were made of in those days? There was an idea called nuclear democracy, or the bootstrap model, and it said all particles are equally fundamental, and they are made up of one another. It's as if somebody said, everybody in this audience is composed of everybody else in this audience. It's a crazy idea also, equally strange. However, quantum mechanics permits such a representation, and people believe that that was the model of the neutron and proton in those days. And of course, in that model, you had no little hard objects inside the neutron and proton. You had smooth charge distributions.
所以那时候的一个可能的解释是，这些所谓的基本粒子呢，基本上都是同样基本的，那没有什么点状的东西存在那边，基本上都是一些很模糊的这个存在。
Now, but the Stargate Quarks occurred between 1968 and 1972 by MIT SLAC collaboration. It utilized the equivalent of a very powerful electron microscope, which peered inside the proton and neutron. The linear accelerator, which provided electrons, gave an energy of 20 billion electron volts. It's as if you took 20 billion batteries and put them in series, and that would be the energy, roughly, of the beam. The effective magnification was 60 billion times greater than with ordinary light, and that is what discovered the quarks. And I'll give you more detail on that.
OK， 那在1968到1972年的时候 ，MIT 跟 SLAC 呢刚好有一个非常强大的这个电子显微镜，它基本上把电子加速到20个 GeV 或者是200亿个电子伏特。那你可以想象把200亿个3号电池串联在一起的能量，差不多就是这种能量。那或者是呢，你可以把它想象成一个电子显微镜，它有这个60个 billion 或600亿倍的放大倍率，所以它们可以用来研究质子、中子的内在结构。
So I'd like to give the names of the people who participated. It was a team effort. The blue names are from MIT, the black names are from SLAC. The thing which is interesting is that the underlying names were graduate students, and they contributed very much to this discovery. And there were 32 people here. The experiment lasted over 7 years, and roughly 9 or 10 participated at any particular time.
这是那时候 MIT 跟 SLAC 的的名单，那蓝色是在 MIT， 黑色是在 SLAC， 底下有一个横杠的是研究生，研究生根据 Friedman 教授说也有非常大的贡献。
And here are the other co-leaders, Henry Kendall, who was a colleague of mine at MIT. Sadly, he is deceased. And here's Richard Taylor, who came from the Stanford Lincoln Accelerator Center, and he's a retired professor at Stanford.
主要的领导者，左边是这个 Kendall， 他是从 MIT 来的，另外一个 Richard Taylor 在 SLAC。
And here's the linear accelerator which produced the beam. It is about 3.5 kilometers long. It was so long it crossed over a major highway and produced very high intensity electrons.
这个是 SLAC 加速器的空照图，它的长度是3.5公尺，它是那么长，所以你可以看到它甚至越过一条高速公路。对不起，3.5公里。
And here are the spectrometers that were used. These were the biggest objects in physics at the time. The long one was 2,000 tons, was 150 feet long. This one to the right was 75 feet long. This is a person here to give you a sense of the size. The target was placed here, and the electrons came in, were scattered, and into this magnet. You could adjust the momentum that was accepted. The detectors were in this concrete bunker, and you would register the electrons. You could rotate these things on these rails to get various angles.
OK， 那这是 SLAC 里面这个磁的分谱仪。OK， 左边那个光那个褐色的东西就有2000吨，大概那边有一个人，所以大家可以看一下它的 scale。 那你可以看到底下有轨道，所以这个 detector 它可以转到不同的角度去做不同角度的测量。
And here's the whole essence of the experiment. Again, it is very simple. In the top, you see this object here is a uniform charge distribution, and the electrons would, if you calculate what the electron scattering probability would be, you would only get small deviations. And this was the proton model of the 60s. This was nuclear democracy. This was what I just described. This is the quark model. This is a model with constituents, substructure. Now, the point is that the quarks were actually 10 times heavier than the electrons, and they could scatter off at a large angle. So large angle scattering implied small constituents in the proton and neutron.
这时候的实验的idea 基本上跟我们之前提到几个都没有什么太大差别。所以如果是这个构成物质是模糊分散开来的话呢，就像刚开始早期的这个布丁模型，所以你这个很高能的粒子打过去的话，基本上是不太会有机会被偏折。但是如果这个原子核是质子中子是由更小的东西构成的话，它会有比较大的质量集中在很小的点，所以电子呢会有可能发生很大角度的弹射。
And here is the scattering distribution. On the vertical axis, we have the probability of scattering. This is the momentum transfer, but really, if this is a technical term, the axis goes as roughly the angle of scattering squared. And this is the distribution one would expect from the old physics, the bootstrap model, nuclear democracy. And this was observed. And you see there is an enormous difference between these two models, which was striking. And when one tried to find out how big the quarks were, they were too small to measure. All that you could do was get an upper limit on the size, and I'll talk about that later.
这些那时候的散射实验的结果，这个 Y 轴呢基本上是发生散射的几率，那 X 轴呢基本上是所谓的 Q square， 或者是可以把它想象成散射角度的平方，所以越往右边走呢，散射角度越大。那中间这个破折线呢，它基本上是这个像布丁模型所预测的。那实验结果呢是在10的-1那附近那些点。那实验结果呢发现基本上跟这个角度没有什么太大关系，所以在那个时候的实验进度看起来呢这些夸克呢是很有体积的，它们是一个点粒子。
So we found small constituents, but the question is, are these small constituents quarks? They could be something else. To prove they were quarks, one would have to determine two things. One, that they were spin 1/2, and two, that they have fractional charge consistent with the quark model.
所以实验看到有很多小小的点挤在这个质子中子中间，但是你怎么知道它是刚刚给我们的夸克模型预测的夸克呢？那你必须要做到2个测量，确定它的确是夸克模型预测的。第一个呢，就是它的自旋必须是1/2，它角动量是1/2 h bar。另外呢，它必须带有的电荷呢，必须是夸克模型预测的2/3跟-1/3。
So the first thing was to measure the spin, and this was easily done. It was a hard experiment, I should say easily done. But by comparing forward and backward scattering, electron scattering, one could determine the spin of constituents for the following reason. The forward scattering depends upon the electric charges primarily. The backward has a greater dependence on magnetic scattering. And so if you take the rate, and the magnetic scattering is also related to the spin. It has a part from the spin. And so you could actually measure it, and spin 1/2 turned out to be the right answer. Any other spin would be quite different. Would be 0, basically.
那怎么确定这个看到的这个小点点呢是自旋1/2的东西呢？你可以用高能的电子实验，那你去看从前面就是往前跑的跟往后面散射的电子，它们的比例是多少？那这边呢，这个实验理论呢有预测，理论预测如果它是自旋1/2的话，你可以看到是在虚线那个部分；如果自旋是0的话，这个东西的比例应该是0。那这个实验很困难，那不过他们做出来的确是这个东西的确是有个 spin 1/2的东西发生了散射。
Fractional charge is much harder to determine, and only can be determined by comparisons between electron scattering and neutrino scattering. And the results came from a large heavy liquid bubble chamber called Gargamel between 1971 and 1974.
你要如何去确定它带有分数的电荷的话，这个实验就比较困难了。你必须要同时用这个电子散射跟微中子散射，同时比较这2个的发生散射的比例呢，你才会有办法决定它的电荷是多少。那时候1971到1974呢，刚好是有一个很大的liquid bubble chamber，叫这个名字可以做这个实验。那等一下他会告诉你更多。
Here is the bubble chamber. It was actually 5 meters long. It contained 12,000 liters of freon.
所以这就是刚刚提到的这个探测器，它有5公尺长，那里面装了12吨的冷媒 freon， 大家可以看到人爬在上面。
And the first thing that they measured was the cross section for both neutrinos and antineutrinos as a function of energy, and they found that the scattering probability was linearly dependent on the energy. And the important point here, so don't worry about the technical aspects, students, but the important point was at this measurement determined that neutrinos were also scattering from point-like objects.
所以这个实验呢，可以去看微中子跟反微中子的散射的结果。那这个横轴呢是微中子的能量，所以从1个 GeV 到100个 GeV， 左边是它的散射的这个几率。那为什么会这样子的话，请进清华大学，然后修我们的课，我们可以告诉你怎么算。那基本上重点是呢，它是一个线性的这个趋势。那这提供了一个更重要的这个hint， 就是就算连用微中子做散射，它看到也是一个点粒子。
Now, this is the important calculation. It's the probability of neutrino scattering over the probability of electron scattering and that ratio, properly normalized, I won't get into the technical aspects of it, because the forces are different, equals 2 over the up quark charge squared plus the down quark charge squared. And if you evaluate that, the number came out to be 3.6. And the ratio turned out to be 3.4 plus or minus 0.7. Now the error is large, but it turned out any other assignment of the charge deviated enormously from that. So that error was compatible with actually discriminating and showing that the charges were compatible with the quark model. And it was just astonishing to people when this was announced. It was, in fact, the person announced it, he said, this result was astonishing. And people were so shaken by it because they had already thrown out the quark model. And it took quite a while for people to accept it. But there were many verifications and many different experiments. And so if you look at the chart here, okay, I'm sorry. My apologies.
OK， 所以你做一些简单的理论估计的话，你可以发现这个微中子散射跟用电子散射取一个特别的 normalization 的话呢，这个理论是预测，如果是夸克模型的话，它的值是 3.6， 实验得到结果是 3.4 加减 0.7。虽然这个实验误差还有点大，不过所有的人都被惊呆了，因为他们早就放弃了夸克模型是一个正确模型，所以就花了人们很久很久的时间去接受夸克模型。那当然，他也提到还有很多其他的电荷测量的实验，他这边没有讲细节。
And so if you look at the conclusion, if you look at it, you see it turns out that the nuclear democracy fails in 2 important categories. It wasn't point-like, and it had no fractional charges. And so the quark model agreed with every aspect of these experiments. And so nuclear democracy faded away between 1974 and 1980. It took a long time before the old point of view was finally discarded and the new point of view was accepted, and that became the basis for the standard model.
所以就算有刚刚这些实验结果，大家还是花了很多时间跟很多的实验呢，去验证这2种不同看法之间的差别。那显然是夸克模型呢，完胜这个 bootstrap model。不管在考虑它的自旋、它的电荷量，或者是它是不是一个点粒子呢，它都完全完胜这个所谓的 bootstrap model。那不过人们还是花了非常久的时间去慢慢接受这个 bootstrap model 是不对的，必须要采用夸克模型。
So now there are 6 types of quarks. There's the up quark, the down quark, the strange quark, the charm quark, the bottom quark, and the top quark. And they all decay ultimately down to the up quark and the down quark. And they all have different masses. In fact, the top quark is heavier than a gold nucleus, which we don't. It's really amazing. They all have fractional charge, they all have spin 1/2. And now, what is the upper limit of the size of the quark? It's of the order probably less than 10 to the minus 17 centimeters. Now, this means, so let me give you a feeling for what that is. If you expand a carbon atom to the size of the Earth, a quark in comparison would be smaller than a half a centimeter.
OK， 那现在呢，我们实验发现一共有6种夸克，有3种是带正2/3的电荷，有3种是带负1/3的电荷。那它们都是自旋2分之一的基本粒子。那它们差别的地方呢，是有非常不一样的质量。譬如说，我们有上夸克、下夸克、奇夸克 ，chunk 是 内夸克，然后 B 是bottom 是底夸克 ，T 是顶夸克。顶夸克的质量呢，有173个质子的重量，所以比金子的这个原子还重，所以非常非常的神奇。那现在夸克的这个大小呢，在我们现在的这个实验精度呢，是比10⁻⁴7公分还小。所以如果你用一个碳原子做比喻的话，你把碳原子放大到地球大小的话呢，夸克大概是2公分以下，那么小。
So you might say, well, you said one of the reasons we didn't believe in quarks was we never found a quark.